In this question, we have a small circuit. It's got a 15-volt battery connected to a 3-ohm resistor. And it says that the right edge of the circuit extends into a uniform magnetic field, 50 milliteslas, that points into the page. You know, it's into the page because of the X's. What are the magnitude and direction of the net force on the circuit? Okay, so this is a current-carrying wire. We know it's going to feel a magnetic field, so let's see if we can sort out how we're going to find that. We know that magnetic force on a current-carrying wire, FB equals IL cross B. L is the length of the wire that's in magnetic field B, I is the current on the wire, FB is the force exerted on that segment of the wire. We know that the current I is important, so let's find the current I before we go any further with this problem. Let's use Ohm's law. So current is what we'd like to find next. Ohm's law says that potential is current times resistance, and then current is the potential divided by the resistance. The 3-ohm resistor is the only circuit element with the battery, therefore all of the potential supplied by this battery is dissipated with this resistor. So there's 15 volts dissipated over the resistor, divide that by the resistance of 3 ohms, and we get a current through this circuit of 5 amps. Okay, now we know I. Now that we've got I done, why don't we go ahead and put in the direction of the current. So it comes out of the positive end. There's our current I. Goes around the circuit this way, down this way, and back in. There's our current I going around the circuit. So for our force, we'd like to find the net force on that loop. To find our magnetic force, we have to do IL cross B for every part of the wire that's in the magnetic field. So if you look at this part of the wire is in the magnetic field, this part is in the field, and this part is in the field. So our net force is going to have a contribution due to the bit of the wire that's on top in the field, the bit of the wire that's on the bottom in the field, and the bit of the wire that's on the side in the field. Let's think about these two guys first, and why don't we figure out if we know what they would be. So right here, from here to here, is the length of this part that's in the field. Let's find the direction. So we'll use our right-hand rule. Thumb goes with the current or with the length. Index finger with the magnetic field. Extended middle finger is the magnetic force. So that's equal to a vector that points in this direction. There's the force on the top part of the wire. Let's call this bit of length here, let's call that L. So the force on the top is I times L times B, and it points straight up. Let's use standard X, Y, Z coordinate system. J hat. Let's do F on the bottom next. So the amount of wire that's in the field is exactly the same length. We'll do our right-hand rule to get our direction. So IL cross B gives a force that points down. There's the force on the bottom. That force is going to have a magnitude of I times L times B. That one points down, so it's minus J hat. So what you see here is that the force is on the top and the bottom of this loop. They cancel completely. Okay, that leaves us with the force on the side. Why don't we draw in our direction first, and then we'll use our cross product to calculate it. So our current comes down, B is into the page, so then our force is to the right. Let's draw that one on there. So when we find our force, we're expecting an answer in the X direction or I hat. So the force on the side is I, L cross B equals our current I is 5 amps. Our length L that's in the field is the distance from here to here. That's 10 centimeters long, 0.10 meters. That length has the same direction as the current, which is down, so that's minus j hat. And then that's going to be crossed with the magnetic field, which is 50 milliteslas. That means 50 times 10 to the minus 3 teslas. The direction of that magnetic field is into the page. Positive z is out of the page, so that direction is minus k hat. Let's multiply our numbers through first. 5 times minus 0.1 times minus 50 to the minus 3 is plus 0.025 times j cross k. J cross k you may just remember, or you may use a tool to remember. J cross k goes with the arrows, so the answer to that is I. So our force is 0.025 newtons I hat. So the force on that wire is to the right.